Oh, could you enable screen sharing?
Yes, I just enabled. Yeah.
Perfect, thank you. Yeah, this works. Okay, is that working? Can y'all see the title slide?
Yes.
Okay, cool. My sound is working this time, so please interrupt me if you have questions at any point, and I'll also have questions at the end. All right, so hi. Let me turn on my camera real quick. All right. Cool. Hi, everyone. My name's Henry. Just like before, same deal. This is going to be a continuation of the last talk I gave yesterday. We're going to move on from static timing analysis in its most basic form of single cycle timing, and we're going to move on to constraints and how you can do more advanced things in static timing analysis. So let's get started. First things first, what are constraints? So constraints are just you telling the static timing analysis tool and other tools in the chain a little bit about your design so it can properly implement it. Some of the big ones are clock definitions is definitely one of the most important. Timing exceptions, not every path needs to meet that strict single cycle timing requirement. We'll get into that a bit later. Input output delay requirements, max delay requirements, a bunch of other stuff we're going to get into. Yeah, but the fundamental thing we're trying to do here is tell the tools, hey, here's some information about our design so that you can properly create it with all the timing requirements that we have. They're typically written in a scripting language called Tickle or TCL. I'm going to show a couple of the commands. The syntax isn't really important. Just want you to be aware that that's kind of how these are done. Okay. I'm going to start off with I/O constraints. I'm starting off with these because they're probably what you're most familiar with. Those of you who have taken CPE 133 or whatever the new, Intro to Digital Design course is, probably familiar with these from the Basis 3 board. If you remember, they had like a Basis 3 masters.xtc file that includes all of the like pin definitions. That's a constraints file. And that's basically just you telling the tool, which in this case is Vivado, hey, these are where I want you to map all of my top level pins to on the physical FPGA chip so that they can talk to the correct peripherals on the board. So yeah, that's literally all it is. If you don't include I/O constraints, the tool will literally just say, well, I'm going to map it to whatever I/O pin I think is easiest, whatever's closest to where it happens to put that logic, which is normally not where you want it. Normally you know where you want your pins to go before you start implementing your constraints. So normally you're going to need to constrain the I/O and make it map the top level I/O pins from your design to the correct top level I/O pins on the physical FPGA die or this physical ASIC die. Okay, clock definitions. This is another really important one. This you are probably also familiar with from Vivado. Basically, you're just telling the tool, hey, these are all of my clock sources, and this is the frequency they're running at, potentially the duty cycle. It's just telling the tool, hey, here's all the information about my clock signals. Please treat these as clock signals because in FPGA land, normally this is automatically, but in ASIC land, you have to explicitly tell the tool, hey, this is a clock signal, and you need to build a clock tree for it. What I have up there, if you're using duty cycle, it's very rare that you'll see a clock that isn't 50% duty cycle. It's only maybe useful if you're using both the positive edge and the negative edge of the clock. I've never seen this, a real use case for this, but in theory, you can have a non 50% duty cycle clock if you're having trouble meeting timing on negative edge stuff specifically. Okay, next up, create generated clock. So this is going to be used if you need to define a clock that is based off of another clock. The common example here is if you have a clock divider. So let's say I have a 50 megahertz signal coming into my FPGA, and then I have a clock divider by 2, so I have a 50 megahertz signal coming out of that. Now, depending on the tool, it might treat that differently, right? Some tools will just say, we'll be smart and we'll say, okay, well, I know that's a clock divider. I know you divide a 50 megahertz, or excuse me, 100 megahertz signal by 2, so that should give me a 50 megahertz signal. It's a 50 megahertz clock. You can just figure it out. Vivado is one of those tools. Other tools are less intelligent and might say, oh, well, you put a 100 megahertz clock into this random circuit and you got a clock out. So I'm assuming that's another 100 megahertz clock, which is not what you want because presumably you're running your design at 50 megahertz because it can't meet timing at 100 megahertz. Um, and in that case, if you're timing it at 100 megahertz, you're not going to meet timing, even if you're only actually running the design at 50 megahertz. The tool doesn't know that unless you tell it that it's running at 50 megahertz potentially. Yeah, create generated clock, very similar. You can see I have a screenshot of the Vivado documentation for it. I'm not going to go into like all of the arguments for it, but generally you specify like, hey, this is they call it a master clock, the source clock. And this generated clock is going to be half the frequency or double the frequency or 3 times the frequency or the same frequency or whatever. You specify the relationship between the two. All right, now we're getting into some of the more interesting stuff. So now we're starting off on timing exceptions. Timing exceptions are basically you telling the tool, hey, there's this path in my design. It does not need to meet the strict single cycle requirement that is enforced by default. So the most simple way to do that is to instantiate a false path and just tell the tool, you don't need to meet timing on this path at all. I don't care how long it takes for the signal to propagate. It could take 10 clock cycles. It could take 100. I simply do not care. There's a couple reasons you might do this. One of them might be because you look at that path and you say, that will never happen. A signal will never need to propagate along that path. I have an example of that up on the slide. You can see we have 2 muxes. We have a signal going in input 0 of one mux, in input 1 on the other mux. And you see they have the same select line, right? So we can agree because these muxes have the same select line, you can never propagate through that path, right? A mux will never forward input 0, and then another mux will never forward input 1 if they have the same select line. I'll be honest, I'm a little unclear if the tools are clever enough to figure out that this is not a timable path by default. You might not need to tell them depending on the tool. I'm a little unsure there. But that's one case where you say like, hey, this path will never be taken. I do not care. Do not time this. The other case is you might have a path that you do care, or rather, it is real, like as in this signal, this path will be taken during your design. But some cases you just don't care how long it takes. Oftentimes, if you have signals that propagate, from one side of your die to the other side of your die, and it's a really big chip, you just aren't going to meet timing on that, no matter how hard you try. And so, from an architectural level, you just have to bear that in mind and know, okay, this signal can show up at any time. It's not timed to a clock. It just propagates as fast as it can, and whenever it gets there, it gets there. I'm just called an asynchronous signal. Um, so yeah, those are sort of the use cases for false paths. The other timing exception that you see a lot are called multi-cycle paths. I'm going to spend a bit of time on this because a lot of people, even at my work, even who've been there for a long time, don't fully understand multi-cycle paths. And you have to be very careful when implementing these, or else you can 100% break your whole chip. So first things first, what is a multi-cycle path? It's you telling the design or the design tools, hey, I want the signal to get there in no greater than 3 cycles or 4 cycles. You're specifying a limit. So it's not a false path, but it's also not single cycle timing. You're saying it could take 2, 3, 4 cycles, a set number of cycles to get there. Okay. And to kind of explain the intricacies of this, I've got a couple timing diagrams here. So the one on the top, you can see this is the default single cycle timing, right? So just to go over this real quick, you can see we have our launch data, we have our capture data. This is not like 2 flip-flops. This is not the output of like, a first flip-flop and then the output of a second flip-flop. This is the output going into the input of another flip-flop. So all the propagation delay used here is just that. It's propagation delay. It's not like it's not caused by flip-flops. Okay. With that out of the way. So you can see that we have our launch data, it launches at some point, and then sometime later, we capture that data. And you can see it takes some time for that data to propagate. There's some time where it's metastable, that's the hashed out area. But it does propagate before the next rising edge. of the clock. This is normal. This is just standard single cycle stuff. Okay, now let's look at the next one. So when you do a set multi-cycle path command, you get to specify whether you're multi-cycling the setup or the hold. So as a reminder, setup time is the maximum time that our signal is allowed to take to propagate. It's our max delay requirement. Hold time corresponds to the minimum time that a signal must take when propagating between flip-flops. It's our minimum delay requirement. So normally, uh, we implement multi-cycle paths because we're having trouble meeting our setup time requirement. And so designers will just say set multi-cycle path dash setup, and then whatever else they need to say to make that MCP work, which results in the tool trying to create a timing diagram that looks like this, the second one. So you can see data 0, this is an MCP of 2, by the way, so 2 cycles. You can see that data 0 is held for 2 cycles, which is something you should be doing if you're doing multi-cycle paths. You should be maintaining your signal stability on the output for however many cycles you MCP'd it for. And then you can see that about 1.5 cycles later, our capture data arrives. Perfect. Okay, so now the tool recognizes that it doesn't have to get there in a single cycle. It has up to 2 cycles to get there. Perfect. What's weird is you'll notice that the launch data transitions from D0 to D1, right, at that point. And you'll notice D0 on the capture side hangs around for a long time. And what that means is the tool is taking such a long time, the tool is requiring that the signal takes such a long time to propagate that that D1 update doesn't hit until at least 1 cycle later. So what it's doing is, or another way to think of it, is that normally our hold requirement, let's say we're running like a 1 gigahertz clock, which means we have a clock period of 1 nanosecond. Let's say our hold requirement is like 50 picoseconds, which isn't unreasonable. Hold requirements are typically pretty small. So let's say it's 50 picoseconds. Well, now we're requiring, the MCP is requiring that that hold be 1 full cycle plus what it was before. So now our hold requirement is 1050 picoseconds, right? 1 clock period plus the original hold requirement. And so we've taken this, minimum delay propagation requirement from 50 picoseconds to 1050 picoseconds, which is a huge jump. And so the tool has to probably insert tons of delay buffers to meet that requirement, to make sure that that signal doesn't transition into a full cycle later. Okay. The reason the tool does this is because this is safe. This generally, you'll notice that none of the data is always stable on our rising edges. And yeah, that makes this a much safer, more cautious approach. The problem is this doesn't help us ease timing that much. Normally, the reason we're implementing multi-cycle paths is because we had trouble meeting the single cycle requirement, and so we need, more slack. We need give the tool a little more wiggle room to meet these requirements. This doesn't give us that much more wiggle room. It does give us some, but not a ton. There's very few circumstances where this is actually what you want in a multi-cycle path. Okay, now let's talk about what most people want or what most people think they're implementing. Okay, from the bottom diagram, moving down, you can see that just like before, it takes about 1.5 cycles for our data to propagate. This is still a multi-cycle path of 2. But you'll notice that immediately after the launch data changes, the capture data goes back to being metastable. It's transitioning. This way, we're keeping the original hold requirement of a very small number like 50 picoseconds. And benefit of this is much easier to meet timing because the tool no longer has to insert this ridiculous number of delay buffers to meet our absurd single or multi-cycle hold requirement. The downside is that now you'll notice our signal is metastable on rising edges of the clock, right? So now we have to be really careful about sampling that data because if we sample it and it's metastable, we can cause, undefined behavior throughout the rest of our chip. So there's 2 sort of solutions to this. Number one, when the signal will be transitioning. Maybe like in this case, it transitions every 2 cycles, it will be stable, and you can use that. Or the other thing is if you don't know when the signal is going to be stable, which is often the case, oftentimes you don't know when a signal is going to change from 0 to 1, you can use a synchronizer, which we talked about very briefly last time, to prevent metastability from propagating downstream to your circuit. So those are sort of the two approaches, but you have to do either you have to do the sort of safe middle multi-cycle approach, which again doesn't alleviate your timing concerns that much, or you have to use a synchronizer with the bottom multi-cycle path approach, or you have to just know when you're going to be sampling that data, and you have to know for sure it's not going to be metastable. Yeah, that is multi-cycle paths. Any questions on that? Just because this is more of a complex topic that a lot of people don't fully understand.
I'll throw one out there.
Oh yeah, go for it.
So when the tool is doing this, you specify that this data will take, n clock cycles. And so what the tool is doing is it's trying to also then make, this is just a clarifying question, the other side stable on whatever your sampling clock edge is?
Yes, depending on which of these approaches you choose. So if you choose the middle approach, it will try to make sure it's stable on all clock edges, all positive clock edges, sorry. If you choose the bottom approach, it will make sure it's stable on the nth clock edge. So the second, the third, the fourth, depending on what MCP you applied.
Got it.
Yeah,
Sorry, go ahead.
let me make some. There is echo, but huh?
If you're talking to me, I can't understand you because of the echo. Okay, should I continue?
Okay. Can you hear me right now?
Yeah, now I can hear you.
Okay, yes, I will just ask question and then I will put sound on the computer. So this is not really a question. This is kind of just information for like everybody that actually Michael like multi-cycle passes are not used frequently. In fact, in like industrial, like larger projects, like networking chips or GPUs or CPUs, even when like multi-cycle passes were put in the past, right now people are trying to convert them into single cycle pass, because when you have like a gigahertz chip which is doing something complicated, this multi-cycle passes become hassle. So like instead we just split long of computation into multiple clock cycles, and you can split even things like a decoder by doing like partial decode, so you can split mathematical operations. So like I see some students who from the start are trying to do designs with multiple clocks and with many multi-cycle passes, but this is usually a bad idea. So usually it's better to figure out how to build with a single cycle and a split of computation and put flip-flops between them. Yeah. So this is like just from my like experience in like three last companies. Because at some moment, like management made decision to just remove all the multi-cycle passes and just insert everywhere flip-flop. And there is also such option as retiming. So Synopsys tools can allow you to specify like some long of computation and just let tool to like insert flip-flops. But this is also not recommended when you do some high performance industrial design. So I saw a project where this automatic retiming was converted into manually inserting D flip-flops to just control everything well. Yeah, so like basically for you as a students, when you do your projects, I recommend you now to stick with a single clock, with a single clock and a single action per clock for the at least first year while you're doing such projects. But like, yeah, so it's, yeah, so like if you just can come here.
I would say I agree with what Yuri's saying, and my experience is similar, but basically what I think Yuri is saying is that the tools aren't good at dealing with multi-cycle paths, so you kind of give up and just make it into single cycle or design things assuming they're single cycle, because actually getting the tool to handle multi-cycle paths correctly is so difficult.
I'm not sure whether tools are good or bad.
Otherwise, you would use it,
Just
right?
introduce additional
So-
complexity in the designs, and we prefer to keep things simple and put complexity in microarchitecture. So to keep things simple in physical side.
Use it.
Maybe I don't know. Okay. So yeah. So like what do you think about it? Let me put sound to computer.
Okay. Can you guys hear me now? Or let me know when it's hooked up.
Yes, we can hear you.
All right. I'm going to go assuming the sound is hooked up properly then. Yeah, so I completely agree. I will say the one place I've seen MCPs used a lot is when the design's already been synthesized, it's already been placed and routed, and maybe we realize, the team realizes, oh, we can't meet timing on this path. We didn't think of this before. Can we multi-cycle path it? Because yes, pipeline stages are, I would say, definitely a better way to go from a microarchitecture specification. But sometimes if you don't realize you have this long timing path until after the design is synthesized, and you're working with deadlines and stuff, it can be easier to introduce multi-cycle paths as sort of a band-aid solution than it is to introduce pipeline stages. I would say, I would not recommend for most students doing multi-cycle paths until you are, well, first of all, you're probably only dealing with them if you're dealing with large chips, large FPGAs or large ASICs, because that's when the propagation delays start to get really big. And yeah, when it takes you like, I don't know, at most an hour to synthesize your design, definitely adding pipeline stages is the way to go, because that's a lot less of a burden. But yeah, I will say though, I have seen maybe not this level of detail of MCPs on interviews, but I've definitely seen conceptually like what are good ways to close timing on interviews, and MCPs are a good answer there, in my experience.
I have a quick question about this slide.
Ooh. Yeah, what's up?
So the middle one is an MCP where you have moved the setup requirement but not the hold requirement.
Correct.
And the bottom one is one where you've moved both the setup and hold requirement.
Yes.
And so the bottom one, you're promising only to capture the data every other cycle or every few cycles.
Yes.
Whereas the middle one, you could capture it every cycle, but then you're asking the tools to do a lot.
Yes. Yeah, exactly.
So generally, the bottom one would be better for a true multi-cycle path.
Yes. Generally, the bottom's going to do a lot more to alleviate timing closure. Yeah. Okay. Unless there are any further questions, I'm going to move on. All right. Clock groups. This is something that is getting a little into the weeds, but I wanted to talk about it because it's one of those things where if you do it wrong, your whole chip will not work. Constraints in general are one of those things where if you don't do it right, your whole chip doesn't work, FYI. It's very important to get them right. Okay, so clock groups, this is all about defining the relationship between your clock signals. If you have a master clock coming in or a source clock coming in, and then that goes into a clock divider and you get a divided clock out, those clocks have a very specific relationship. They're what we call synchronous or phase aligned. And it's fairly easy to route signals between them. So long as you tell the tool correctly, hey, these are, this is my source clock, this is my generated clock. The generated clock is half the frequency. The tools can figure that out. When you get to more complex scenarios, let's say you have let's say you're communicating on like a high-speed interface like PCI Express, and when you do that, you usually get what's called a recovered clock, which is the clock that is recovered from the incoming data on the PCI Express bus. Usually you have that, and then usually you'll have like a system clock that defines, the logic for 99% of your, defines the clock for 99% of your logic. Those two clocks are not going to be synchronous 90% of the time. They're going to be completely unrelated, completely different frequencies, and completely different phases. And so you would define those clocks as asynchronous. What gets tricky about that, though, is when you define clocks as asynchronous, the tool says, well, I don't have any ability to time things between asynchronous clocks. Like, I don't know what you want me to do. And so it does nothing. It just says, well, I'm not going to time this, and it takes however long it takes, and I don't care. Now, that's fine because you can put in your own constraints to define how long you want to take signals to propagate, but you have to make sure you do that. The onus is on you to define the maximum and minimum delay requirements for those signals. That's really important to go over. The next thing is logically exclusive and physically exclusive. This is kind of getting into the weeds, so I'm not going to spend a lot of time on it, but these are other forms of asynchronous clocks. Physically exclusive means you're telling the tool basically, hey, there are no paths between these two clocks. None at all. I'm just telling you about this so you can do some fancy crosstalk calculations. If you don't know what that means, don't worry about it. It's like, again, getting really into the weeds of physical design and VLSI. And if they're logically exclusive, you're basically telling a tool like, hey, these two clocks appear on the same net, but not at the same time, right? So that might be like, oh, I have a clock coming into my circuit. It's either 50 megahertz or 100 megahertz. The way you tell the tool about that is you define two clocks, 50 megahertz one, 100 megahertz one, on the same net, and then you just tell it, hey, they're logically exclusive. And that also has some crosstalk implications. And to sort of cap this off, you have to be very sure before setting clocks as anything other than synchronous, because if you set them as anything other than synchronous, the tool will not time paths between the clocks, and you can run into issues like that. Okay. Oh, I see. I got it. Okay, I just saw the question in chat. Sorry, I'll answer that when I get to the end if that's still if people are still wondering about that. Anyway. Okay. And these are all the other constraints. So these are sort of smaller ones that are pretty simple. So I'm just going to go over them all. Bang, 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 bang. First of all, we have I/O delay constraints. That's basically telling the tool, hey, it's going to take this signal this long to get from its original input to the boundary of my chip. This is important because if you're trying to run a 100 megahertz SPI interface, for example, that would mean you have, 10 nanoseconds clock period. If it takes the tool 10 nanoseconds to route the signal from, your logic to the edge of the chip, well, it still has to go off board, off die, and get to whatever peripheral it's going to. So you need to set some margin there. And that's how you do that, is with set max delay. Or excuse me, set input and output delay. Also set max delay, which is often used for clock domain crossings. When you have two asynchronous clocks, you need to, explicitly tell the tool, hey, make sure this signal propagates in less than X nanoseconds, not clock cycles, nanoseconds, because the clocks are asynchronous. And when you're dealing with two asynchronous clocks, the concept of a clock cycle is sort of meaningless. There's also set max skew, which tells us the tool, hey, I have these like, 3 signals, let's say they're all part of one 3-bit bus. I want them to arrive within 500 picoseconds of each other, right? So that's another big one. That is all the sort of miscellaneous constraints I had. Let me make sure to answer the question in chat, and then I'll open it up to general questions. Henry, can you please explain how do we know which approach we need to use among top or bottom approach for any multi-cycle path in our design? Okay, sure. So let me go back to the multi-cycle path thing. Come on, come on, come on. So the question is, how do we know which of these approaches we should be taking with multi-cycle paths? Went too far. Generally speaking, you're always going to want the bottom approach. The reason I'm talking about the middle approach is because it is sometimes necessary if you're dealing with single cycle pulse signals. So if a signal is only going to remain valid for one clock cycle and you can't like stretch it to remain valid for multiple clock cycles, that is the rare use case where you're going to want this middle one. The bottom one's generally what you're going to want because that's going to do a lot more to ease timing. And generally, if you're targeting a multi-cycle path, that is your main goal, is to ease timing. So yeah, that's that question. Hope that made sense. Any other questions? All right, I will take that as a no. Or my audio isn't working, but I think it is. So yeah, one thing I did want to talk about, but it looks like I'm out of time, is how. Okay. For my master's thesis at Cal Poly, I did a lot of work to try to get some FPGA servers from Western Digital up and working. I'll just give you the highlights. They're like, I think there's 14 servers. Each of them has 4 FPGAs in it. Each FPGA is somewhere in the neighborhood of like $50,000 to $100,000. They're like top of the line FPGAs. They have like 200 times roughly as many flops and LUTs as the Arctic 7s that we use. They're monstrous FPGAs. They actually have each FPGA has 4 dies on it because they're so large they can't like economically put all the logic on one die. There's 4 of them. They're absolutely monstrous machines that Western Digital was probably using for like emulating entire ASIC designs and putting that on FPGAs. All that's to say, they're really cool. There's a lot of unique design challenges that come with them, namely getting them working because we don't really have a lot of documentation on them, or at least we didn't. I tried to do something to rectify that. The reason I'm telling you about this is if you're at an FPGA hackathon, you're probably interested in working on stuff like this. So if you are, a student who's taken like 333 and have, some experience with FPGAs and stuff, and you're interested in these, you should definitely either reach out to me or Stephen Beard, who's my advisor, who's sort of looking for people to continue these things. Yeah, really just shameless plug. They're cool machines. They're worth a lot of money. It's a very unique opportunity, I would say, for, undergrad or even grad students to get to work on machines like this. So if you are interested, please reach out to me or Stephen Beard for doing like projects on these things. They're really cool. And I see I have another chat message. Thank you. Okay. With that, unless there are any further questions, I think I'm going to hand it off to Cisco. Let me stop sharing. Yeah.
Just a moment. I have a couple of additions. Okay. Need to get a different mic. Yeah. So one so one thing is that, like as I said yesterday about CDC, that usually like CDC are used between like larger blocks. Like if you have like multi-core cluster with a coherent cores, like type of processor used like in phones or in some like 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 a home routers and so on. With those type of CPU, you may run the whole core on one clock and like coherence manager block, which coordinates, which makes sure that cores do not conflict in like memory reads and writes. This may run like on different clocks. So then you need to put some handshaking between them using special techniques, which you can read in Cliff Cummings' article, crossing clock of the main crossing, or like also Cliff Cummings asynchronous FIFO. So usually, like I don't recommend when you study this, like immediately to put multiple clocks for different computations and combine designs. So this is one thing what I want to show. And another thing, I just want to illustrate how this large, expensive prototyping FPGA boards look like. So I have actually slides about this. So let me find it and show it. Second. So let me share my screen. Yeah. So. Yeah. Okay. So if you yeah, so this is types of prototyping FPGA boards with the Cooper scale, which cost like $100,000, like $300,000. They're using most to prototype ASICs. So when you when like simulation takes too long and you want to run your like CPU or something else you're building with some like long runs like a booting Linux, you can use such a prototyping FPGA boards. And in addition to it, FPGAs, they're also used in emulator. So emulator is a device which is similar to such prototyping boards, but have better access to the internals like of your design. So with like emulator, you can actually see like create a waveform and see what is going on like in the middle of this like Linux boot on not yet created CPU. So let me show you examples of emulators on the web. So one is called Zibo. This is called Yeah, so see. Yeah, so this is example of such device for prototyping ASIC, which is created by Synopsys. So this is box filled with FPGAs. And they use like ultra scale FPGA. So also there are emulators which are not based on FPGA, which is based on special ASICs like Veloci emulator. This is also box. So this thing Veloci box is a high-end version, costs like several $1 million. So but like many companies, they buy. So they call like large companies Intel, Apple, Samsung, Nvidia. For like design groups, they usually have this thing like a Zib and Veloci, just like standing somewhere in the room, and for GPU, like we use them to run some like benchmarks with realistic frames, like what you have like in a 3D game on a computer. So like in a picture from a game, you can see like several million of triangular primitives. So like each of them is floating point coordinates and so on. So to simulate such things in software, this would take days, but with emulator, this takes just hours. And same thing with things in CPU companies for like booting Linux. So this is one of emulator, specifically in case of Zibo, is one of prime use for those very expensive high-end FPGAs. But the principles used there are the very same as principles used with this like educational FPGA boards you're using. Yeah, and also I need to mention Cadence emulator. Palladium, I think the new version Cadence emulation platform here. They have Palladium emulation. So this is also sort of like specialized kind of a supercomputer. So this can emulate like up to 48 billion gates. So, but this thing is not based on FPGAs. This thing is based on specialized chips, which task is just to like emulate your like Verilog design as fast as possible. So this is the kind of tools you are using, like used by like engineering teams in like large companies and in some startups, like I was in like AI accelerator startup which had Veloci emulator, and like there are some ideas of businesses of like renting emulation time to the startups, but so like I'm just saying this because yesterday there was question of what emulator is. So actually this is what like emulator is. With FPGA boards you have limited access to what is going on inside, but with emulator it synthesizes your Verilog in a way that you have much better signal visibility. But one last important thing about emulator is that timing in emulator, because it's FPGA specialized ASIC, has nothing to do with the timing of a finer ASIC. So emulator are used only for functional verification on cycle by cycle behavior. So just like what you do in the RTL-based simulator, you verify cycle by cycle, and in parallel, you look to the report from static timing analysis to make sure that your logic fits in a clock cycle. Yeah, so this is addition about emulators. Okay. Okay. So
Hi. Hello? You guys good? Okay, let's move on to the next presentation then. Hello again, everybody. Today we are going to talk about, well, I'll just show you. Let me share. So today we're going to talk about memory repair. So this is kind of continuing in the kind of more advanced topics in ASIC design and ways that it is different from FPGA design. And so kind of the goal here is to understand some of the differences in priorities between industrial and academic chip making, right? So in academia, we're really focused on novelty. We're focused on making things that are new and cool and that we can get published for, or just kind of, you know, experimenting and making cool stuff, right? And so we're trying to make stuff that's high performance, but we're also trying to make stuff that's simple enough for students to understand, simple enough to be maintained. And so this leads to a lot of really cool experimental stuff, but it also sometimes misses some of the aspects that are more important in industry. So in industry, we're really concerned about yield, which really refers to the percent of chips that we make that are actually going to work, right? So whereas in academics, if we tape out 100 chips and 20 of them work, that's, you know, 20 cool things we have to show off. If we do that in industry, our 20% yield is not going to be good enough for our customers. It's not going to be price effective. And so we're going to probably lose our jobs. And so as another piece of this is cost and reliability. We need stuff that is not going to fail on our customers. We need stuff that is going to last a long time and not be too expensive to make. And then finally, we care a lot about bring up time. Whereas, you know, if you're doing a PhD or a master's, you have maybe a year to try and do bring up on a chip. Whereas in the industry, we really want each chip to take, you know, as little time as possible to minimize that cost, you know, 30 seconds per chip, make sure it works, send it off to be used, right? And so as a part of exploring this difference, we're gonna look at some techniques that are employed in industry to bring up increase the yield and lower the cost, increase the reliability of all of the chips that come off of our wafer. Okay, so we have to talk about SRAM because it is one of the main components that takes up area on a chip. Many chips, especially more recent ones, can be upwards of 80–90% SRAM, right? So we can see for reference here some kind of both older 130 nanometer and kind of new-ish 40 nanometer chips. All the boxes are SRAM. There is a lot of RAM on chips. And SRAM is great because it's super high density. You know, only 6 transistors per bit of memory is really small, and they're really small transistors. The problem with it being so small is that it's extra error susceptible. So if you have one tiny little imperfection in your wafer that hits, you know, one of these little tiny transistors on an SRAM cell, suddenly that cell might not work. And that is going to cause problems. So on these really big chips that are mostly SRAM, it's like, you know, throwing darts at a dartboard. You're going to hit some SRAM. You're going to see some errors. And so how can we make sure that getting some errors on your chip isn't going to completely ruin your chip, right? That's kind of the goal. And so to understand this, we need to understand kind of some of the ways SRAM can fail. So the easiest to detect faults are stuck at faults, where a certain bit is just stuck at 1 or 0. So no matter what you write or read to this bit, it's always going to show a 1, it's always going to show a 0. And this can be easily accomplished just by, trying both possibilities per bit. And these are pretty easy to detect. What's harder to detect is what's called a coupling fault. And this is where doing an operation on one cell will impact its neighbors, right? So if I write a bit to one cell, maybe a cell 1 row over or 1 column over is also going to get written. And that's going to be pretty bad, because those are kind of harder faults to detect. And so we can see, for example, what some of these faults look like. So we can have, neighbor coupling, we can have, and that can be missed if we're only trying to write 0s or 1s. And so what we end up having to do is write some kind of checkerboard pattern across our chip and use that to discover if cells are stuck at or if cells are coupled to one another. And so there's a couple ways we could do this. We could do this externally with a debugger and just, have some debug interface that slowly goes through every SRAM cell and reads it and writes it and then sends that data out back on some interface. And we could do that, but that would be pretty slow. And it would be really nice if we could just turn our chip on and know right away, or know relatively quickly, whether or not there are errors in the SRAM, right? And so this brings us to a concept called BIST, or sometimes MBIST, which stands for built-in self-test, or memory built-in self-test. And that's just going to be a little tiny state machine that lives right next to our SRAM that's going to read and write this checkerboard pattern across all of these cells in the SRAM, right? So 1 row at a time, we're going to write 1s and 0s and then switch the order and then read all the nearby rows and make sure that there's not coupling. And so that's going to record for us where all of these bit errors are, and without us having to do a ton of external interaction. It's just going to automatically at startup do that. So that's what makes this the BI and the built-in self-test. It is hardware that we're putting on our chip that's goal is to test our chip, right? And so what do we do with this information? Okay, we know like a bunch of SRAM cells are dead. Great, are we gonna throw the chip away? Well, not quite. So what we can do to get around this is start adding redundancy to our SRAM, right? So we can have a big giant column of SRAM, and then on the side of it, we can have a spare column. And maybe this spare column will also be SRAM, or maybe it will be a higher reliability memory, like a flip-flop or something. And so as we find a fault, we can kind of shift over what counts as our SRAM and use a bunch of little muxes to select different columns. And so we can do that for both rows and columns. We can add more redundant spare columns, or SCs, and more redundant spare rows as well. And the more spares we add, the more faults we will be able to overcome, but also the more decoding logic that it will take, right? If we only have 1 spare column, we can accomplish this with just 1 mux on the output of all the columns, right? If we do this with a lot more, we're going to need a lot more muxes, a lot more logic, but we get a lot more redundancy out of it. So now we have a way to actually use a fault to recover, which sounds pretty simple, but it ends up being a little more complicated. So if we only have like 1 spare, it's pretty easy to say, well, if I have 1 error, I can recover from it. And if I have any more errors, I'm just screwed. But what happens when we start having like, 3 spare rows, 2 spare columns or something? How do we analyze where our errors are and how we can correct them? So this brings us to the concept of BIRA, or built-in redundancy analysis. And so what we're going to do here is algorithmically assign our spare rows and columns in a way that will cover all of our faults, right? So this picture on the left side is the output of our BIST, our self-test that tells us, hey, here's all of the column faults and all the row faults. And we're going to feed this information into our little BIRA algorithm And that's going to tell us how we can assign our spares in a way that takes care of all of the faults in our memory. So on the right side here, you can see we've assigned 3 rows and 3 columns in a way that the spares cover all of the X faults, right? And so now this memory is just going to work as long as we're correctly muxing which rows and which columns we use. So BIRA is going to go through our memory, take the results of our test and then assign spares so that our memory is now repaired. And so because of this structure of using rows and columns, it's actually less of a consideration of how many errors we have and more a consideration of what shape do the errors take. So like if we had 1 row and 1 column of spares, we could not fix this one on the left because there's no way to replace 1 row and 1 column and have it fix all of those issues, right? But on the right side, even though we have a lot more errors, because they're in a shape that we can cover with spares, assign the middle row and the middle column to be spares instead, we can fully recover that shape on the right. And so that's kind of what BIRA is doing, is evaluating, are we recoverable or is this chip dead, basically? And so putting this together, we get to this concept of memory repair, or BISR, built-in self-repair. So we're going to run BIST when we start up and figure out where all the issues with our memory are. We're going to feed that result to BIRA, which is the algorithm that assigns where the spares are. And then now we have this information that lets us repair our memory and assign those spares. And we've just turned a broken memory into a working memory. And so this is great, but it does take a while to run this test, right? We do still have to access every bit in our memory multiple times and look at its neighbors. So we don't really want to have to do this process every time we start up. And to be able to not do it every time we start up, we're going to have to store this information somewhere. So we're going to want to do this BISR process one time and then store those results, hopefully on chip, right? That way we can just turn on our chip for the first time and it will completely repair itself. And so where do we actually want to store these results? Well, it turns out there are a lot of ways to store permanent memory on a chip. There are expensive and high density ways, and there are also cheap and low density ways. So depending if this was the kind of thing where every time you boot up it was a different set of errors, you would want some kind of memory that you could use over and over, like eFlash. But because these errors are basically the same per die that we get, every unique die will have its own set of errors that won't really change through the lifetime of that die. And so that means we only ever need to store the result once. We only need to run this process the first time that chip ever gets power, and then we can permanently store that result somewhere. And so often what we'll do is we'll store that in an eFuse. Now, what the heck is an eFuse? Well, you can see from this chart, it can only be written one time, and it's pretty low density at like maybe 4 kilobytes or less. But that's okay because we don't really need that much information to store. We just need, one offset per kind of spare that we're going to get. So not a lot of bits to store to make this happen. So what the heck even is an eFuse? Well, an eFuse is a non-volatile storage that you can only write one time. And the way you write it is by blowing a fuse. So we can see on the left side, we have on our dies, we have these long, thin strips of metal, and we are going to use a slightly higher voltage than usual to build up some charge on one side, and then we'll blow the fuse, and now it will permanently store a 1 instead of a 0. And so this is a really useful way of very cheaply permanently storing something on our chip. And the great thing about this compared to ROM is it can be done after tape out. So you can tape out, get your chips back, and then still permanently store some information that varies per chip that you get back, right? Sometimes we also want to store high security information like a unique key on each of our chips. And for that, we might use a different kind of fuse, like an anti-fuse. The only real difference there is whether or not you can look at this chip in a microscope and see how it's programmed. But for the sake of built-in self-repair, we don't really care if anyone looks at our chip under a microscope and sees how we're repairing our memory. So we're just going to use the classic cheap normal eFuse. And so putting this together, we're going to start up. We're going to find faults with our BIST by writing those checkerboard patterns. We're going to pass that output to our BIRA algorithm and figure out, I have X and Y spares on my rows and columns. Can this chip be salvaged, or can it be repaired, or do I have to throw it out? And then we're going to write that result to our eFuse. So we're going to have some finite state machine that's pretty tiny that is just going to go through our eFuse and blow each eFuse to represent the bits of which rows and columns are going to be replaced. And so once that is completed, we can report that to some debug interface. Often this will be a JTAG tap controller, or just some kind of interface that the person doing bring up is using, and it'll just tell the person, hey, this chip got repaired, or this chip doesn't work. And then I know, as the guy doing bring up, do I have to throw this chip away, or can I move it on to be used on a board somewhere? And so this is kind of really complicated, and we haven't won any new features out of it. Our memory is still the same size. It's not any faster. In fact, it's probably a tiny bit slower. All of this stuff that isn't increasing performance, but is super increasing our yield and our reliability of our chip. And so kind of the reason that I wanted to talk about this today, and just in general, even if you don't exactly need to use BISR on your small academic designs, the point is that there's a lot of work and complexity that goes into fault tolerance in industry chips. Improving yield is really important, and designing for test is really important. So as designers, we should be going into this process thinking about, when I get this chip back, how am I going to debug it? How am I going to make sure that it works? Because even if we design it perfectly, we'll get it back from the manufacturer and it'll have some issues, and we'll have to debug those issues. So there's a whole world of DFT, or design for test, that should be explored and has room to grow in the academic and especially open source levels. So yeah, basically just when you're doing designs, think about how you can debug them and how you can make them more reliable after they've been taped out. And these are things that you never have to think about on FPGA because they've already been handled by whoever did the ASIC design for that FPGA. But as any of you who are aspiring ASIC designers need to really think about what goes into bringing up a chip and making sure that errors are recoverable. So with that, I'll just open it up to questions about this process or about design for test in general.
So this is one specific example of design for test or a fault tolerance measure.
Yes.
How many different types of examples are there for these?
There are tons. So at ASIC companies, there are full teams whose whole job is design for test. A lot of what gets done is scan chain work, where every flip-flop in your design gets also hooked up in a big shift register so that you can debug every single flip-flop in your design. There's a lot of work that goes into JTAG boundary scan, which lets you read and write the every I/O pin on your chip. There's a ton of work that goes into SRAM redundancy, like this. This is one example, but this is an example with one RAM. Imagine you have a chip with 50 different RAMs of different sizes. How do we handle that? So there's a ton of research you can do into this field, and also a ton of jobs in this field. If you're interested in things like, how do I make chips more reliable? There's even whole companies whose purpose is to provide other companies with intellectual property that does these kind of things. There's a company called Protein Tech, for example, whose whole thing is telling you, is this die that I got back from the manufacturer faster than usual, slower than usual, or average. It'll characterize the die for you, save you a ton of time of sorting, is this die good or bad? And so, yeah, there's whole companies whose only job is to build intellectual property and sell it to other companies to do these kinds of things.
Yeah, let me add a couple more things to it. A second. Turn off. Okay. So, yeah. So let me add a couple things to it. Yeah, so Cisco was talking mostly like about BIST for static memories, and it's true that like static memory occupy like a lot of area on the die, and we use like by the way, yesterday we like mentioned the FIFOs, and also today like Alex will talk more about this because this is some critical knowledge you have to have. But yesterday FIFOs I demonstrated in system Verilog we're using flip-flops, but actually once FIFO gets larger than like a few thousand flip-flops, so like let's say like FIFO which is like 100-bit wide and like 30 deep, like it's already candidate for putting into SRAM, because like any like large memories inside your like ASIC design, it's better to put in SRAM because like SRAMs are smaller than this amount of flip-flops. SRAMs consume much less power, and so with a SRAM, you also can build like a SRAM-based FIFO, or like those SRAMs are used in design like everywhere. So if you are doing like network chip, then you're getting a bunch of Ethernet transfers from different ports, and then you form a packet, and before you do like editing of packet in hardware, you need to store them somewhere. So you store in like in both like multi-bank internal SRAMs and pieces in FIFO when the storage is like overflow. Oh, 1 second. Yeah, so when like a SRAM store, so when you don't have space in like flip-flop structures like FIFOs or something, you store in like SRAM based FIFOs, or 1 second, something is with I think I will just turn off this. Turn off this and just use regular speaker. Okay. Okay. So Cisco, can you hear me? So can somebody say that whether you hear me on Zoom?
Yeah.
Okay,
Yeah.
good. Yeah. So what I want to say is that like SRAM, they do occupy some portion of die, because when you need to store some like pieces of network packet, or when you need to store some set of like triangles in GPU you're going to process, you use various SRAM for some local storage needs. And you like even build FIFOs using SRAM, but because like SRAMs may have latency, you need to put some logic around to use them as some microarchitectural elements. But post-silicon debug is not just BIST and is not just a scan chain. So scan chain just means that you connect the flip-flops in your design like into a chain which you can like extract information and just see what is going on.
Flip-flops or SRAM, or even like would you do it for DRAM too, or is it only S?
We usually don't put DRAMs into designs I'm dealing with. So I simply cannot say from experience, because like SRAMs are very important, because when you even start the design, when you get architecture specification from like architecture team and need to write micro architecture specification, we like one of our first steps is that we need to determine sizes of SRAMs we need, and so that physical design team can start working in parallel to like place them in a floor plan. With DRAM in things I was working on, DRAMs were usually external, and there was even like HBM memory, which is like high performance memory outside, which is used especially in like networking chips to store like tons of like internet traffic and have like fast access. But in addition to, so BIST is used to like check and repair memory, and then there is a scan chain used to extract current state of design from the chip and figure out what is going on in certain seconds. But this is not everything. As RTL designer, you also need to give tool for team which is doing post-silicon debug, which is debug of chip after after foundry. And in order to do this, you explicitly put in your Verilog some flip-flops which are accessible by software. So software driver, when they can read and write some memory mapped registers, and those registers connected to your flip-flops. And then bits of those registers will tell you various information what is going on in your design. If some FIFO gets full, or if something gets stuck in your final state machine, or whether your state machine went into some wrong state. And so like usually this like post-silicon debug team, also chip is already manufactured, they send me like email like, Yuri, what bits in register can we use to determine whether transaction is stuck in your block or somewhere else, or what your block is waiting for. Because maybe like my block send a request to get some information about, let's say, some like colored triangles. You need to get data from another block, and it's just stuck waiting for this data. So then they need to send the mail to person who is handling another block. And like tells it, like Yuri says that he sent you this number of transactions, and his block is just sitting there waiting for a response. But within like 1,000 clock cycles, this like response never come. So now it's like a ball is on your side, so you need to figure out what is going on in your block. So you need to put such debug registers in your design when you design, so that after manufacturing, this is kind of first they make like test chip, but then they can make like final chip. So this is useful to debug test chip. But even this also can be used to make software workaround. For example, if you find that something got stuck because it was not properly implemented, we put so-called chicken bit. So chicken bit means that if you did some optimization, but you are not sure it's going to work, that even if you make mistake which went through all the verification, you can still fall back to old version of design by flipping chicken bit, which is like also associated with this debug. And then this will work, maybe not as good as you wanted it to work, but for user, it's better to have something which works like 2% slower than not have devices this year at all, you know. So this is like some addition for debug in addition to BIST and to scan chains. Yeah.
It's called a chicken bake, right? Because it's like insurance. It's like you're scared.
A chicken bit, chicken bit, yeah. So this is like in a game of chicken when like people put like cars to each other who first to so get scared. So like chickens that we designed this block, but we are scared that at the very last moment on the like release of our product on the Las Vegas Consumer Electronics Show, person will come to the podium with the telephone and it will just die, you know. So like in order for such thing not to happen, you need to have chicken bit as insurance that in the worst case you will use some older design, you know. So this is one thing you need to think about when you do design. Yeah, there are also some like even more exotic things like there are some spare bits you plan in your design which can be used in like ECO, which is like engineering change order, which is done after chips is synthesized, placed and route. When you have everything and you suddenly realize that some small group of things do not do what you want to do. So, and they can do some finer change on like physical errors, like surgery in chip. But this is not like after manufacturing. This is before the manufacturing. So this is actually a different story. Okay, so let's continue. Yeah, so let's break for lunch, and like other presentations you have, let's do it after lunch. So can you hear?
Yeah.
Francisco? Yeah. So what other presentations do you have?
Oh, I'm done with presentations. I'm not sure if there are other people with any.
Okay. Okay. So so what about your colleagues? So like are they done?
All right.
Yeah. So
Henry is
what
done
about
as well,
your
yes.
colleagues who wanted to do presentations? So are you all done?
As far as I know, everyone I've talked to is done, but I'm not sure if there are other people.
Okay,
that
good,
you
good,
have.
good. Yeah, this is fine. So we'll continue like after lunch, but yeah. So thank you very much. So this was very useful and done in a like very good manner. So this was like to the point with like all the necessary details and in like a clean, understandable way. So yeah, yeah. So thank you very much. Yeah. And we will now continue mostly working with the boards, but like Alex also will talk about FIFOs, and then you will see FIFOs on the board and in simulation. Then we'll talk about challenges and interview questions. Okay, so thank you, and we will interrupt for the lunch.
Yeah, thank you.
Yeah, there are some questions in chat. So yeah, so let's join back online at 1 p.m. Yeah. Mm-hmm. Mm-hmm. Yeah, FT team logic. Yeah. Okay, thank you. So let's disconnect.